Okay, so the first exam is a week from today. So let's talk about that first. Thursday, the 22nd. And the topics for that are going to be problems like the vector review, particle free body diagrams, particle statics, and rigid body free body diagrams. But no calculation, so that means that if you look at the rigid body free body diagram problems, those are only 2D. There's no 3D problems. So, and you won't have to do any Newton's laws, although really, like almost everything in this class, if you get the free body diagrams right, you're halfway there. But that's it. It looks like a lot of topics actually, but the free body diagrams problems don't have, there's not too many of those. And so the quizzes have been, the quizzes are two things. Short answer questions about what I say in lecture, and then redoing problems that you've done on the assignments. The exams are only problems, and the way to get ready for the exams is to make sure you understand why you take every step that you do in those assignment problems. Okay, so working through those assignment problems is the way to get ready for those, and you should do each one definitely more than once, more than twice probably. You know, just make sure at every step, like ask yourself, do I know why I'm doing this? Like, don't fall into the rut where you're like, okay, I've already done this problem. I remember this was negative, and that's that. You know, like, why did you take each step? And if you understand each problem to that level, you're going to do great on the test. Yep.
I know you said this at the beginning of the semester, but how long do you expect your exams to be? I.e., we have 90 minutes. Do you plan for a 60-minute exam?
Yeah, that's what I plan for. So I try to, the thing that I think about as I do it, as I write it, is I want half the people in the class to be gone after 1 hour. Okay. That's what and then half stay for the other 20 minutes or whatever. We don't have 90 minutes because there's a class right after us, but we probably have 85, you know, but yeah. I try very hard not to make them like races against the clock. Any other questions about the exam? Okay. Well, we don't, like I said, we've already covered all the stuff that we need to cover for the exam, so I'd be happy to answer any questions about homework or anything that you have today. When we're done with questions, we'll go on to the new stuff. Same thing Tuesday. If you bring questions Tuesday, I can answer homework questions. Anybody have any questions about homework problems?
Actually, just one other general question.
Yes.
Will there be any homework due before the exam?
Let's see. I think it's due on the day of the exam, the next homework assignment.
Okay.
Yes. Yeah. Okay. Can I borrow your... Free body diagrams. Yeah, how many of these have solutions posted and how many don't? Let's just do all the ones that don't.
Oh, I think for that one it's all of them. I don't know. I didn't.
They're all posted? Okay. Okay, rigid body, free body diagrams, number 5. So at one end, this beam is connected to the ground by a pin and slot joint. And at the other end, it's connected by a pin joint. And then in the middle, there's a pulley that connects to the ceiling on one end, and on the other end, it connects to the beam. Okay, well, this one is a little, I should have made this a little more clear about what I wanted you to isolate. There's really 2 interpretations you could make. Let's do them both. One is to isolate the beam only. That's the one that I guess it sort of suggests that you want, but that really would most likely not be the most useful thing to isolate if you were trying to do a problem. The second interpretation is isolate the beam and the pulley together, and when I do that, you'll see why that's more useful probably. Okay, so first, beam only. There's a weight. It doesn't say what the mass is, so I'll just call that mg. And now we're just going to go around the boundary looking for contact. I'll start down here. The first thing we contact is the pin joint at the right end. A pin joint produces a full force vector of unknowns. So draw the component directions, and then I'll write that as, so you could write that as the force on the beam by the pin or on the beam by the ground. It turns out that that double subscript notation only helps you if you're going to isolate the other body. So when things are connected to the ground, I tend to just call those R, RA, RB, or whatever. So it's your choice here. It doesn't hurt to use this double subscript notation, but I'll call it force on the beam by the ground. Actually, the ground, now that I think about it, that's not going to be specific enough. Force on the beam on the right. And then if we keep going around, the next thing we contact is the base of that pulley. What type of joint is connecting the base of the pulley to the beam? That's a fixed joint, right? You see that the base of that pulley, it can't translate, it can't rotate. It's like glued or welded to the beam. And so what kind of loads are applied by a fixed joint? So there's a force vector because there's no translation allowed. And is there rotation allowed? No, so that means that there's also a couple. So at the fixed joint you have a force vector that I'll call the force on the beam by the pulley. And there's a couple that I'll call M on the beam by the pulley. Any questions about that? To see the picture?
So couple opposite, and what are the two forces that are acting in like a couple moment?
You can think of it as, so here's what's going on with the couple. If this is like a blown up section of the beam, and this is the base of the pulley, one side of the base of the pulley is applying a force down, one side is applying a force up.
That's by the nature of the pulley, or?
That's by the nature of the joint. That's just something that we know that if you weld something, you know it can do that. What's an example?
So it's kind of like us sitting on a chair. There's our weight acting down, and then the normal force acting up.
That's not quite the right analogy. Let me try to do. Let's think of one. Think of a beam connected to the wall, okay? And think of pushing down on the beam. Okay, that beam doesn't go anywhere. So how is it that it doesn't go anywhere? So there's the force acting there. There's a force that the wall applies acting there to counteract that. But the other thing it has to counteract is the fact that this force is trying to cause a rotation, right? If this was a pin joint, that beam would just swing down, right? So in order to counteract that tendency to rotate clockwise, this fixed joint has to apply a force this way and an equal and opposite force this way that produces the moment that keeps it from rotating.
I have a weird, I don't even know if this is
Yeah.
possible in the field. Like, so what if the pulley was perpendicular, or
Uh-huh.
if it was parallel to the beam, and there was no, then there wouldn't be a moment, right? Because it,
If it was parallel to the beam, so what does the base look like? What the connector look like?
I guess it's easier to think of like as a weld joint. If a weld joint was just like you had two bodies, it would just act as one body.
Yeah. Okay.
Never mind.
Okay. Any other questions about that? These, understanding how these joints work is going to be kind of like the heart of this class, and it's confusing for everyone at first, and it'll hopefully get more clear as we go. And now, keep going around and we get to the pin and slot joint. The slot is horizontal, and so the force applied by the ground, by the pin, has to be perpendicular to the slot. And so you can apply it this way. Actually, I missed one thing. I skipped. So here's the connection from the base of the pulley. Go around here. The next thing we actually hit is where the cable attaches to the beam. And so that's a pulling force. It's parallel. That force is parallel to the cable, away from the chosen body, so that way. And then the last thing we have is that force applied to the slot. I'll call that R. You could draw that up or down because a pin and slot joint can apply a force in either direction. Which way you draw it determines what the components of your unit vector are. But you'll get the same answer either way. We'll see that in examples. Any other questions about this? Yep.
How important is the notation? Like, for example, if you have R versus, I don't know, random variable
Yeah.
N,
Yeah.
would that be wrong?
No.
Or?
No.
Okay.
The notation's important when you use the double subscript vector notation. The other stuff, no, R, N, or F, they're just, it doesn't matter.
Because that's one of the things I always noticed when I was looking over the homeworks is I'd have the notation wrong somewhere and it would be R when I was using F.
Yeah, right, that's not a big deal.
Okay.
I would get in the habit of using T whenever you have tensions, but other than that, it doesn't really matter.
Okay.
Yes?
I didn't get why the subscript vector FB on why we drew like one to the right and one going upward. Right?
Well, anytime you have a force where you don't know the direction, the way you represent that in a free body diagram is you show that one component is in the direction of positive x, you show the other component is in the direction of positive y, and you represent it with a vector variable.
Oh, okay. But how we don't know the direction of the joint?
You don't want to try to guess at the direction. You just want to put in these in the positive x and positive y direction. The math is going to come out on its own. So say that you knew that the components of this force were going to be this way and this way. Okay. What this is saying is that your first component in your vector variable, a positive value is pointing this way. And it screws up your whole way of using vectors. So you don't want to guess, is the answer. You just want to do that.
Oh, okay. Okay. And the body we don't know where it applies, so we put them the same.
Exactly. Yep. So you always draw it like that. Yes?
I guess I'm kind of confused between what's like considered a vector versus like a scalar
Yeah.
force, because I guess I don't understand what a force would be without like a direction.
Okay. So you're right. All forces have directions. All forces are vectors. Sometimes, going into the problem, we know the direction of that force. And so we indicate that in our free body diagram by just drawing an arrow in that direction. Then all we don't know about the force is the magnitude. Okay? And so instead of representing this force as a fully unknown force vector like this one says we don't know anything about that force. We don't know how long it is, and we don't know the direction. This, we know the direction. We just don't know the magnitude. So we represent the magnitude by a scalar. We say this could be 50 or 150 or 600. We don't know that, but we do know that its direction is this. It is still a force vector. It's just we know more about it, so we represent it differently. Does that
Yeah, that makes sense.
help? Okay.
Sometimes I always put like the little vector
Okay.
sign above all my forces, and I
Oh, okay.
want to make sure I get that wrong.
Yeah, don't do that, because we want to be clear that if we know the direction of a force, the variable we have associated, like all we don't know, is a single number. Whereas here, we don't know any components of this force. So this notation tells us that there's one variable here, and this notation tells us that there's two variables. And if you're careful about that, it'll make it a lot easier to figure out whether you have the right number of equations, right number of variables that you can solve for. Okay. Any other questions about this one? I just thought of, let's change this to 3 interpretations. The third one is we're going to isolate the beam and the pulley and the left half of the cable. Okay, so let's go to the second way of interpreting this question. So this time, we're isolating the beam, and we're also including the pulley in our chosen system. That's part of our chosen body. There's the weight. Keep cruising around counterclockwise. You have the force on the beam by the right part of the ground. Then you get to the pulley, and now we don't have to deal with the contact forces between the pulley and the beam because those are internal loads. All we have to deal with is the fact that the cable leaves our chosen body here and here. And now keep going around and you get to the spot where the cable leaves the end. So that's another T because that's a single cable going over pulleys. And then you get to the bottom and you get to the force on the slot by the pin. Yes?
Would those two T's to the left side cancel each other out?
They do cancel each other out, and that you would see that when you went into the equations, which is kind of the reason why probably the best way to isolate this if you're trying to solve a problem is the third possibility where we're also going to include that stretch of cable. But any questions about this one? Yes?
You denoted R on the left side. You noted it as, mentioned it rather as force slip by the pin.
Yeah.
How can you denote that R as force vector of
Yeah. Because this is a force in a known direction, and so this is a scalar variable. And scalar variables, we don't want to use that subscript notation because it's a million rules, you know? And like, just little by little, you have to remember these rules. Like, all we're trying to get to is the point where, like, you don't think anymore. You're just like, you see this stuff. Remember in Terminator, where they're like, he looks at stuff and it shows what he sees, and it's like, sink, person to kill, you know, whatever. That's what we're trying to do. We're just trying to get to the point where, like, you see this and you're like, fixed joint, you know, force vector and couple, cable, scalar variable, you know what I mean? Like, all of these things, we're just trying to follow the rules, and you just have to internalize a million rules.
So that reminds me, so what I really want to do is I really want to like memorize the joints and then what their vector notations are, but
Yeah.
I have a feeling that that's like going to not be as useful in the future when it gets more complicated, or is that useful?
No, that's the way to do it.
Okay.
Yep. That's the way to do it.
So
Every time you see a fixed joint, do it in this voice, too, in your head. Be like, fixed joint, couple. I think that voice helps you remember it.
I do have a question. So basically, speaking on the left side, when R is pushing this way, and there's play, how we know that force, like the scalar force that R is pushing this way?
We know that it's pushing one of two directions.
Okay.
We know that the force applied to the slot is perpendicular to the slot. But I could have drawn it this way, or I could have drawn it straight down.
Oh, okay.
If you look back at the notes from the joints from last time, it says for a couple types of joints, it says this value can only be positive and only in this direction. For this one, it says it can be positive or negative, which means it can be in two directions. So you can choose which way to do it. The math will make it come out the same.
It's better to choose it in the positive.
I don't think there's any reason to make a distinction. That's just the way I happen to draw it.
So when we're solving for our R variable, when it's like perpendicular to the beam, it would just, when we solve for it in the math, that would follow our regular coordinate system where positive would be up and negative
Yes.
would be down? Okay.
Right. And, yeah, let me not say anything anything else about that right now. Well, I think as we do example problems, how to treat this in the math will, be more clear. Any other questions about this second interpretation? Yes?
So, in general, when I saw this question, I wanted to just say, like, things would cancel out, but the point of this is basically we're doing all of the forces there, regardless of, like, if it looks like they're not doing that.
Yeah, right. Don't, that kind of goes back to the last thing. I think one of the things that you want to avoid in this class is really too much guessing about what's going to happen, Just follow. We just want to get to the point where you follow the rules, go through the steps, treat every problem the same way according to the steps, and just trust that the math is going to deal with all those kind of things. Yes?
So, is there like coupled force, like moment force acting on it in the second part, or would we neglect that?
No, the reason we neglect it is because this force FBP and this couple MBP, those are forces applied to the beam by the base of the pulley.
Oh, okay.
And here, the base of the pulley is internal. And so what happens when, it's not like those forces don't exist anymore, but now because it's internal, we have FBP acting on the beam by the pulley, and we also have negative FBP acting on the pulley by the beam, and they cancel out. That's why only the external loads matter.
We care about the tension on the pulley, right? Like
That's all we care about because that's the external stuff.
External.
We only care about the external things. The internal things all cancel out.
Okay.
Any other questions about? Yes? This one? Uh-huh. Yes, to do a problem, you need to know that angle, yeah. Well, it turns out when we do the third interpretation that you don't need that angle, but you would think so, now that I think about it. So I'll show the third one after we're done with questions on this one. Yes?
Sorry, I was asking the last question, but I'm still a bit confused. So basically, if we have the beam and we neglect the pulley, we just draw the force on the beam, but we have in the problem we have a pulley acting on it. This way, if we don't put the pulley with the beam, like in the first, we draw a coupled force.
Yeah, I mean, you just always have to. So you isolate the body, and then you just look for what kind of joints are connecting the body you isolated to the outside world. So in this case, if we're just isolating the beam, when we see this joint here, we see that the beam is connected to the base of the pulley. We recognize that that's a fixed joint, and then we follow the rules of fixed joints to determine what loads go there. Any other questions about the second way of thinking about it? And now the third way, the most helpful way, most useful way, is we're going to isolate the beam and the pulley and the left piece of cable. It's a little hard to draw. Okay. So this is our free body. Do you follow what that's supposed to be? There's the pulley, and we're also including in the free body the cable, the stretch of cable going from here to the end. So here we have the weight. Over here we have the force due to the pin joint. then we get to the pulley, and there's a force acting up that cable tension. But now these other T's are internal loads, so those don't appear. And then we have this R here. And so what's the benefit of the second and third interpretation compared to the first one? Well, you can see it by just counting the variables. We want as few variables as possible because every variable that we have means we need an equation to solve it. And equations are a limited resource, you know. Newton only made so many laws. So here we have 1, 2, 3, 4, because those are vectors, right? Each of those have two components. So 1, 2, 3, 4, 5, 6, 7 variables. To solve for all of these loads, we need 7 equations. Here we have 1, 2, 3, because those are all the same T, 4. Way better, you know. We've eliminated the need for 3 equations. Same thing here, even though it's simplified the math a little bit. 1, 2, 3, 4 variables. Notice that you still can't solve this. So how do we know that we still can't solve this? Well, that's true. But how many equations do you get in 2 dimensions from Newton's laws? 3. You get 2 from Newton's second law, 1 from the rotational equation. We have 4 variables, and so there's nothing we can do. Yes?
If our mass was known, then we could do it, right?
No, because I didn't count that as a variable.
Oh, yeah.
It's one way to think of this is called statically indeterminate. There's no, you can't use statics alone to solve this problem. And one way to think of that is, could we, 1, 2, 3. So, for example, if we replaced this this unknown cable tension with a known cable tension, so we reduced the ability of this thing to support loads by 1. Okay. You can picture what would happen with this system, and it would still be static. It still wouldn't be able to move. In other words, there's like redundant joints keeping this locked in place. And if there's ever any joint that you could remove, or a part of a joint you could remove, and the thing would still be static, you know it's statically indeterminate because that unnecessary, you don't know how much load that unnecessary joint is taking. I'll talk about statically indeterminate stuff a little more soon. Any other questions about that one? Do you want me to go through any of the other ones in the free body diagram practice problems? I know there's solutions, but if I do it up here, I can sort of explain it as I go, you know.
Is there another example in there that has multiple interpretations?
No, I think that's it.
So when it comes to problems where there are multiple interpretations, do we just pick whatever interpretation we feel most approaching? I
think the answer is those tend to be pretty complicated problems. And in complicated problems, sometimes you start down one road, see that things are happening that you don't like, and go back and start over again. That's not going to come up in this class very often. It comes up more often in real problems, you know. I should point out that even though this first interpretation is more of a pain, you could still solve it this way. You just find that after you set it up like, well, if you could solve it at all, you could still solve it this way. It's just that after you isolated the first thing, you'd realize you also had to isolate the base and the pulley itself. You'd use Newton's third law, so these variables wouldn't be new. And so you'd have twice as many equations, twice as many variables, but you could still solve it that way.
If we were asked to solve, draw free body diagram, the force acting on the beam only, so we lose only the first interpretation, right?
Right.
If it's
Yeah. Yeah, so if that was on a test or something, I'd have to be more specific about what I was asking for. Okay. Well, let's just do some more rigid body problems. They have free body diagrams in them anyways, so. Okay, so let's say that there's a beam that's connected to the wall by a fixed joint. And this angle is 50 degrees. And on the left end of the beam, there's a cable that goes over a pulley. And that cable is connected at the other end to a 200 kilogram mass. And the length of this beam is 2 meters. Oh, and also the mass of the beam is 100 kilograms. So we want to know what are the cable tension and the reactions on the beam. Well, the first thing I'm going to do is isolate that 200 kilogram mass. So we have a downward force of 200 times 9.81. That's 1962. And what other loads are acting on the box?
Tension.
Yep, the tension is pointing up. Anything else? Nope. So we did the weight, we went around, there's only one place the outside world's contacting it, so that's it. Okay, and then Newton's second law says 0t, because that's in the positive y direction, plus 0, negative 1962 is equal to zeros. The first equation doesn't help. The second equation says t is equal to 1962. So we know that cable tension. One thing that I like almost everything about doing statics before you do dynamics, but the one thing that I don't like is if you're not careful, it can make you careless with how you treat cable tensions. If this was so in every statics problem, it turns out you'll see that in a setup like this, that cable tension is just always equal to the weight of the mass. And so you're going to get, it's going to be sort of natural, enticing to be like lazy about it and just look at it and say that that cable tension is the weight of that box. If this system was dynamic and accelerating, that would not be the case. Okay? So I would much rather see you keep enforcing the habit of isolating the mass, calculating the cable tension, and then going on. Because in dynamics, that's the only way to get the right answer. Okay. Well, now we know the tension. So now we can isolate the beam. At the middle of the beam, we have the weight. So that's 100 times 9.81. Over at the wall, we have a fixed joint. So what kind of loads are applied by the wall? A couple and a full force vector. So I'll just call that R and M, or MR, I guess I'll call it. You could use the subscript notation, but like I said earlier, if we're talking about a connection to the ground, there's no point in doing it because we're not going to ever isolate the ground. And then keep going around, and eventually you get to where the cable connects over here. What's the direction of that cable force? It's up, and we know the value of it now because we calculated it. So that's, this is also T because it's the same cable, which means this is 1962. So now I'm going to write out the table. I'm going to do the abbreviated one, but I think I'll go back after this and show the full one just so you can see the two ways you can think about this. I think this is the one you want to sort of gravitate to in the long run. But so the first thing we have to do to fill out this table is choose an about point. So what do you want to choose as an about point? Yeah, you want to choose the connection with the wall. It doesn't make, choosing another spot doesn't make the answers wrong. It still works. It's just going to simplify the math a little if you choose your about point where you have the most unknown forces. So that's here. And so once we choose the about point, if we're using this short table, we think about the origin of the coordinate system being here. And then our row vector is just in that coordinate system at the about point, the coordinates of all these other points. Okay. So the row vector, well, so okay, our origin is at this red dot. I'm going to start by dealing with these loads at the wall. So the row vector going from A to the point where R is applied, from the origin here to where R is applied is 0, right there at the same spot. The force, this is in 2D, so Rx, Ry, 0. Take the cross product, 0. Now we also have this couple acting at the wall. That just goes in the moments column, and the other stuff doesn't matter. It doesn't produce a force. Now we'll go to where the weight's applied. The row vector is just the, if you think of the origin being at the wall, then the row vector is just the coordinates where this force is applied. So what are the coordinates of this location given this origin? I guess we have to figure out, we have to think a little bit about that angle. So think of it like this. Yeah, like it has no width. Yes, that's right. Okay, so it doesn't change too much if you do deal with width. It's just a little extra geometry you have to do. But okay, what's the angle theta for this red vector? It's positive 90, 180, 270, minus 50, backtrack 50. So what's that, 220? So this is going to be, well, and this distance is 1 if we're just going to the weight. So it's going to be 1 times cosine of 220 sine of 220. The force vector is 0, negative 981. And then 0, 2. I'm doing these all in 3D. And if you take that, if you calculate that, that vector rho and take the cross product, you get, I think you get like 1501, negative 1501. So 0, 0, negative 1501. Does that make, that doesn't make sense, does it?
Yeah, it's 751.
Okay, half of that. Okay.
That must be for the 19th.
Oh yeah, you're right. 751 positive. Does it make sense that that moment is positive? Yeah, if we're treating this as the pivot point, then that force is going to make it rotate counterclockwise, so that's positive. And then the last one, what's the row vector, or how do we calculate the row vector? Yeah, so now the length is 2. So it's 2 times cosine and sine of 220. The force for this one is 0, positive 1962, 0. And for this one, we get 0, 0, negative 3002. Any questions about that table?
So why didn't you have on the diagram, you have a pulley hanging down, right? And why was, you didn't have a free body diagram for the pulley, so.
Yeah, if we did a free body diagram of that pulley,
Because it looked like you didn't
Yeah.
include the pulley was isolated.
no, you're right. So in these, I think the short answer is when we do these problems where there are pulleys attached to the ground, you're never going to isolate the pulley. If you think about how complicated it is to isolate the pulley, because of, like we saw it in this last example, all the extra variables that we got by separating the pulley from its surroundings, we'd have to deal with that if we isolated the pulley. We could do it that way, but it wouldn't help us. We just don't want those extra variables. So the way to do problems like this, and there'll be a lot of problems that look sort of qualitatively like this, is we're going to isolate the mass, we're going to isolate the beam, and any pulley that's attached to the ground, we're going to leave that alone. Okay, so Newton's second law. We're going to take all the forces in this column and add them up and set them to 0. So Rx, Ry, I'll leave off the third component because that equation would be useless, plus 0, negative 981, plus 0, positive 1962 is equal to zeros. And you can solve this right away, and you get that the r vector is equal to, the x component is 0, and the y component is negative 981. So you have one equation that says Rx plus 0 is equal to 0, a second equation that says Ry minus 981 plus 1962 equals 0. Just solve those for the two components. And then the moment equation, I did one thing here. The only thing that I didn't include all the components of was that couple, just out of habit. So let's write this as 0, 0, mr. All of these are just z components when you're in 2D. So for this one, I'm only going to add up the z components of the moments. So we have 0 plus mr plus 751 minus 3002 is equal to 0. And so mr is equal to, what do you get if you subtract that? 2251. The force is in newtons. The moment couple is in Newton meters. Yes?
So that means that the joint MR it's rotating this way with 220 or 2,251 Newton meters to counteract the pulling or the upward force.
Yeah, right. The pulley is trying to, this cable that's attached to the pulley is trying to pull this beam up. And so in order to prevent it from rotating clockwise, there has to be a counterclockwise moment applied by the wall. Okay, so now I'm going to, any other questions about that? So now I'm going to redo the beam, using the full, the pancake table thing, I'm going to just choose an origin and do everything, calculate the coordinates of everything and use that in this table. And the coordinate system I'm going to use is on the wall, straight across from the end of the beam. Okay. I'm just going to do that to show how this works if you're given coordinates in some arbitrary coordinate system. Okay, so the first thing we have to do is calculate the coordinates of all these points. So let's call this A, B, and C. This is the coordinate system. We know that this angle is 50 degrees. So this is 40. So let's calculate these coordinates. To get the coordinates of C, that's just going to be, 2 times the sine of 40. So what's 2 times the sine of 40 is what? 1 point, sine of 40, 1.29. Who knows what I'm doing here? Anybody? You follow what I'm just trying to, so I just have this coordinate system, and I'm just trying to calculate the coordinates of these 3 points, okay? And then we're going to go from there. So, was that right, 1.29?
Yes.
Okay, so the coordinates of this point C are 0x, 1.29y. The coordinates of A are just negative 2 times the cosine of 40, which is like negative 1.53. And then to calculate the coordinates of B, you could do some funky trigonometry, or you could remember that to get the midpoint of any 2 points, you can just average the 2 points. So the average of these 2 points is negative 0.76, I'll say 766, positive 0.643.
So if the length would have been 4, then you would have multiplied, half of that would have been 2. You would have included that into the...
Uh-huh.
How is C 0, 1.29 recorded and how did we do it?
That's just the height from the x-axis to C. So I just use this green right triangle. The length of this beam is 2, so 2 times the sine of 40 gives you that height. Okay, so pancake, artist, row, 4, marzipan.
Are those things using an about point, or is that
Yes.
origin going?
Nope, we can choose that about point separately from the coordinate system.
Okay.
And So let's take the about point. Well, what are we going to, let's choose this as the about point just to see how it works out differently. Okay, and because that's also called A and the about point is called A. Okay, so go back to this free body diagram. The first thing I want to treat is this force R. So what are the coordinates of the point where R acts? Not anymore. In this coordinate system, the coordinates where R acts are 0, 1.29. So 0, 1.29, and I'll keep it all 3D, so I'll just add zeros in the Z. What are the coordinates of the about point in this coordinate system? Yep, negative 1.53, 0, 0. Now to get the row vector, you just subtract those two. So 0 minus negative 1.53 is positive 1.53, 1.29, 0. The force vector is Rx, Ry, 0. Take the cross product of those, and you get 1.53 Ry minus 1.29 Rx, and that's in the Z component. And then we have the couple. So we cancel all this stuff and just put this in as 0, 0, MR. The next force is the weight force. What are the coordinates where the weight force is applied? Yep. So that's the weight force acts at this point B, and those are the coordinates. So negative 0.766, positive 0.643, 0. The about point has to stay the same, so that's negative 1.5300. If you subtract those two, you get positive 0.766, positive 0.643, 0. The weight force is 0, negative 981, 0. And what's 0.766 times negative 981? Okay, negative 751. That's what we called it before. I'll leave it like that. And then the last one is that cable force. What are the coordinates where that cable force is applied? Yep, that's at A. So negative 1.5300. The coordinates, the about point, have to stay the same. So subtract, and you get 0, 0, 0 for the row vector, which we knew because any force acting at the about point has no row vector. The row vector is from the about point to something. And then the force is 0, positive 1962, 0, and there's no moment. So Newton's second law says Rx, Ry plus 0, negative 981 plus 0, positive 1962 is zeros. And that tells us that this r vector is equal to 0, negative 981. And the moment equation says 1.53 times ry, which we know now is negative 981, minus 1.29 rx, which is 0, plus mr, minus 751, plus 0 equals 0. Can someone calculate mr for me? It looks like it'll come out about right. 751 plus, 20, so mr is equal to 2251 Newton meters. The equations came out looking a little different, or the moment equation came out looking a little different because we chose a different about point. But those are the two ways that you can organize your results to calculate this. So think about, is there any time that you would think it might be useful to write out this full table as opposed to just calculating based on rho and f? That is getting at the right thing, yeah. I mean, even if your about point is chosen for you, you can do this because you're just trying to calculate. You know, you put your origin at the about point, whether it's chosen for you or not, and do it this short way. But if you're ever given a problem where you're given all of the coordinates of all the points, which could happen in a problem like if you have like a system of members connected by joints like this, you could go into the problem by being given the coordinates of all these points. Then since you already have all those points sitting in front of you, it might make sense to do it this way instead of recalculating all those row vectors cold. But for the most part, this is just a faster way to do it, I think a better way to think about it. Okay, let's do one more quick one. So let's say that we have a pin joint connected to the ground on the left. And the beam goes to the right. There's a pin in the center that's connected to a slot, and the slot is angled at 45 degrees. And there's a downward force of 1,000 newtons. Let's neglect the weight of the beam. And calculate the reactions. So a free body diagram of the beam. We're neglecting that. We're neglecting the, and you don't need the mass in this in statics because there's no MA term. In dynamics, you would need it anyways. But, so okay, there's a 1,000 Newton force acting there. There's a force applied to the pin by the slot. That's perpendicular to the slot, and you can do it either way. So I'll do it like that. I'll call that RP for the reaction at the pin. And then there's a pin joint on the left. That's a full unknown force vector. I'll just call that R. So I'm going to write this out as rho, force, moment. I'll choose my about point here. So think of that as the origin. So with this as the origin, what are the coordinates where R is applied? 0, 0. Yep, zeros. The force is R, X, R, Y, 0. Cross product is zeros. With this as the origin, what are the coordinates at the pin in the middle? Oh, I didn't give a length, so that's unanswerable. Let's make that 1 meter. Okay, so what are the coordinates at the center?
0.5.
Yeah, positive 0.5, 0, 0. That force, remember you have to put the coordinate system at the tail. So what's the angle for that vector? Negative 45, yep. And so that's going to be 0.7071 RP, negative 0.7071 RP, 0. And so the cross product is 0, 0, negative 0.3535 RP. And then what are the coordinates of that 1,000? So 1, 0, 0. The force vector is 0, negative 1,000, 0. The cross product is 0, 0, negative 1,000. Newton's second law says Rx, Ry plus 0.7071 Rp, negative 0.7071 Rp, plus 0, negative 1,000 is equal to zeros. The moment equation says negative 0.3535 Rp minus 1,000 is equal to 0. So what's negative 1,000 divided by 0.3535? 2029? Oh, 2829. Negative, right? Newtons. And then what's 0.7071 times this RP. Just take this, plug it in, and calculate negative 2,000. And what's our Y? The top one should be negative because there is a that RP.
Because RP can be negative. And then
Oh, RP is negative, right? Yeah, you're right. So they're flipped. So that one's positive, that one's negative.
RX is negative. RY is positive, I think that's right.
Yeah.
Because RP is negative. So
RP is negative, so RP is actually pushing this way. And so RX has to be pushing this way to counteract. Okay, that's all.
Yeah, because it's solving, okay.
Yep.